The morning of May 14th, 1942, at Aberdeen Proving Ground in Maryland. A dusty testing range stretches empty under grey skies, and scattered in the dirt near a scrap pile lies what looks like plumbing supplies. 5 feet of steel tube, open at both ends, roughly welded to a wooden shoulder stock that appears salvaged from a surplus rifle. Wire coat hanger sights bent that same morning with bare hands and a broken nail. The entire contraption weighs 13 pounds and cost approximately nothing to build. At the far end of the range, a captured German Panzer rolls back and forth, simulating an armoured attack. Between 5 different weapons development teams and this moving target stand the careers of desperate army engineers and the survival odds of every American infantryman who'll face German steel in the coming years. Lieutenant Edward Ewell shoulders the crude tube assembly. He aims at the Panzer using sights made from scrap wire. He pulls the trigger. An electrical charge ignites a 3.5-pound rocket inside the tube. White flame roars backward. The projectile streaks forward at 280 feet per second, trailing smoke. It hits the tank dead center. Then Ewell's superior, Captain Leslie Skinner, grabs the launcher and fires again before the Panzer completes its turn. Another direct hit. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The officers watching from behind sandbags go silent. 5 competing spigot mortar designs just failed to hit that same moving target even once, not a single shot connected. But this improvised tube weapon, assembled from scrap metal and desperation, just scored 2 consecutive hits using sights fabricated from a coat hanger 20 minutes earlier. Major General Gladion Barnes, Chief of Research and Development for Army Ordnance, walks down from the observation area. He takes the launcher from Skinner. Barnes shoulders it, aims, fires. Direct hit. The other visiting brass officers fire the remaining rockets. Every shot connects. The Panzer's painted steel surface shows 6 fresh impact marks, clustered within 3 feet of each other at 75 yards. Barnes makes a decision that will reshape American infantry doctrine faster than any weapon development in military history. He orders 5,000 units. Immediate production. General Electric in Bridgeport, Connecticut receives the contract that afternoon with a 30-day deadline, May 20th, 1942 to June 14th. 1 month to transform a prototype made from scrap into thousands of combat-ready anti-tank weapons. This is the story of how 2 army engineers solved a problem that was killing Allied infantry by the thousands, designed a weapon from components they found in a junk pile, and got it into soldiers' hands in 60 days. Not 60 months, 60 days. From wire coat hanger, sights to the beaches of North Africa. Let's go back to understand the problem they solved. Early 1942, American infantry has no answer to German armor. The United States entered World War II 4 months earlier, after Pearl Harbor, and army planners face a crisis that threatens to lose the war before American troops even reach Europe. German tanks are shredding Allied defensive positions in North Africa, the Soviet Union, and everywhere armor meets infantry. The tactical reality is brutal and simple. When a Panzer division attacks, Allied foot soldiers die or run. The German Panzer III carries 50 mm of frontal armor. The Panzer IV has 80. And infantry carrying anti-tank rifles that can barely scratch 21 mm under perfect conditions watch those tanks roll through their positions like they're not even there. Britain's anti-tank rifle, the Boys, weighs 55 pounds. Requires 2 men to operate. Kicks hard enough to break. Collarbones. Penetrates 21 mm of armor at 100 yards if conditions are perfect. Flat angle. No sloping. Specific steel composition. Combat conditions are never perfect. Against a Panzer IV's 80 mm frontal plate, the Boys' rifle is about as effective as shouting at the tank. The Americans have it worse. Their designated anti-tank weapon in early 1942 is the 50 caliber M2 Browning heavy machine gun, the same weapon mounted on aircraft and half-tracks. Against moving German armour, it might as well be a slingshot. The rounds bounce off. They leave scratches. Some units carry sticky bombs. Explosives you're supposed to run up and physically attach to a tank's hull by hand. The survival rate for soldiers attempting this manoeuvre is exactly what you'd expect for someone sprinting directly toward a 30-ton machine gun platform. The British Piat projector launches a 2-pound bomb using a massive spring mechanism, effective range about 100 yards, requires 40 pounds of force to cock, frequently fails to penetrate even when it hits. One British sergeant in North Africa describes it as a drainpipe loaded with hope. The French use rifle grenades. The Soviets employ anti-tank grenades requiring soldiers to close within 20 to 30 yards, throwing distance from machines bristling with machine guns firing 792 rounds per minute. By late 1941, after watching entire divisions collapse under German armoured assaults in France, the Soviet Union, and North Africa, every Allied War Department receives the same desperate message from every combat theatre. Give infantry something portable that kills tanks, or prepare to lose this war one shattered company at a time. The casualty statistics make the mathematics clear. During the Battle of France in 1940, German armour demolished Allied defensive lines specifically because foot soldiers possessed no effective counter to tanks. The problem isn't tactics. The problem isn't courage. The problem is physics. Infantry bringing 20mm penetration capability to an 80mm armour fight. American Army ordnance in early 1942 faces an engineering challenge with immediate strategic consequences. Solve this before American troops land overseas, or explain to families why their sons died helpless against machines they couldn't damage. The specifications seem impossible. Create a weapon light enough for 1 or 2 soldiers to carry into battle, powerful enough to penetrate 80mm of hardened steel armour, simple enough that soldiers can learn to operate it in days, not months, cheap enough to manufacture by the thousands immediately. And do it before the war moves past the planning stage into actual combat, where American infantry will face those same panzers that are currently destroying British and Soviet formations. The deadline is measured in months, maybe weeks. The industrial capacity exists to build whatever engineers design. The raw materials can be allocated. The soldiers are training and will ship overseas regardless. The only missing piece is the actual weapon. This is where Captain Leslie Skinner enters the story. Skinner isn't some desk-bound theorist. He spent 2 decades working with rockets, mostly on his own time, using salvaged propellant and scrap parts because official Army interest in rocket weapons was essentially zero until Pearl Harbor made everything urgent. Born in San Francisco in 1900, son of an Army surgeon, Skinner built his first rockets as a teenager. This hobby got him banned from further experimentation after he set fire to the hospital roof at Fort Strong, Massachusetts, in 1915. He attended West Point, graduated 1924, commissioned into the Army Air Corps, qualified as an airship pilot. Got assigned to Aberdeen Proving Ground in 1932, where he found exactly one other person in the entire United States Armed Forces conducting rocket research. He spent years producing sketches and proposals for rocket launchers. Every proposal rejected. The official response in December 1940, when he submitted a tube-launched anti-tank rocket design. Interesting concept. No suitable warhead exists. Project declined. Then, in 1942, somebody hands Skinner an M10-shaped charge grenade. This is a recent development. An explosive device using a copper cone to focus detonation energy into a superheated jet that can burn through armor like a cutting torch. The M10 weighs nearly 4 pounds. Too heavy to throw by hand, too heavy for rifle grenade launchers. The only proposed delivery method is for infantry to run directly up to tanks and place the grenade on the hull, manually, which is suicide disguised as tactics. Skinner looks at the M10 and immediately recognizes he has his warhead, the missing piece. He'd been working on rocket motors for months, small solid-fuel engines that could theoretically propel a shaped charge warhead to a target. The experiments produced mixed results. Some rockets flew straight, Some tumbled. All of them created a massive exhaust backblast that would injure anyone trying to throw them. You couldn't hand-launch a rocket motor powerful enough to carry a 4-pound warhead. The exhaust would burn your arm off. This is the problem Skinner hands to his assistant, Second Lieutenant Edward Uhl, in early spring 1942. Find a way to launch these rocket grenades without killing the operator. Uhl is barely out of engineering school. He's been in uniform for months. His entire job consists of 50% of the United States Army's rocket research program. The other 50% is Captain Skinner. Uhl spends weeks testing different approaches. Hand-thrown rockets with protective shields, rifle-mounted launchers using the Springfield's bayonet as a guide rail, small mortars. Nothing works. Either the exhaust burns the operator, or the weapon is too heavy, or accuracy is hopeless, or some combination of all three problems. Then, one afternoon, Uhl is walking past a scrap pile at their workshop. His own later account, probably embellished but essentially accurate. I was walking by this scrap pile, and there was a tube that was 5 feet long and 60 millimeters in diameter, which happened to be the same size as the grenade that we were turning into a rocket. I said, "That's the answer. Put the tube on a soldier's shoulder with the rocket inside, and away it goes." The concept is deceptively simple. A hollow tube, open at both ends. Soldier loads the rocket grenade into the rear opening. Rocket motor ignites while the projectile is inside the tube. The tube contains and directs the forward thrust while allowing exhaust gases to vent safely backward, away from the operator. The soldier stands behind and slightly to the side, aims the tube like pointing a rifle, pulls, a trigger connected to an electrical firing mechanism. The rocket completes its motor burn just as it exits the front of the tube, travelling at nearly 300 feet per second. Uhl fabricates the first functioning prototype in days. 5 feet of salvaged steel pipe, a wooden shoulder stock cannibalized from rifle parts. 2 hand grips, one containing a trigger mechanism connected to batteries stored in the stock. Wire coat hanger sights bent with pliers. Total construction cost maybe $30 in materials. Total construction time about a week, including testing and modifications. They conduct initial firing tests into the Potomac River in late April 1942. The launcher doesn't explode. The operator survives uninjured despite initial fears about backblast. The rocket achieves reasonable velocity and demonstrates that shaped charge warheads can be delivered this way without detonating prematurely. These results are encouraging enough to request a formal demonstration. This brings us back to Aberdeen Proving Ground, May 14, 1942. Skinner and Uhl arrive unannounced at a scheduled test of competing anti-tank weapon designs. The Army has assembled 5 different spigot mortar systems, all designed to launch the M10-shaped charge grenade at tanks. These mortars represent months of development work by established weapons manufacturers. They use sophisticated aiming systems, precision-machined components, carefully calculated ballistic tables. The test protocol is straightforward. Each weapon fires at a moving Panzer target at 75 yards. Hit the tank, prove the concept works in field conditions. Skinner and Uhl set up at the end of the firing line without identifying themselves. They have 9 rockets with dummy warheads, no official permission to participate, no assigned testing time, just 2 officers with a tube made from scrap and enough confidence to demonstrate it in front of Army brass. The 5 spigot. Mortars fire first. Every single design misses the moving target. Some projectiles fall short, some sail wide. One appears to tumble in flight and detonates on impact with the ground 30 yards from the Panzer. The accuracy is so poor that observers begin discussing whether the entire shaped charge delivery concept is fundamentally flawed. Maybe infantry simply cannot engage moving armor at these ranges with any man-portable weapon. Then Skinner and Uhl's turn arrives. Except nobody invited them, so technically there is no turn. But the target Panzer happens to roll toward their position to make another run, and Uhl shoulders the tube launcher, aims with his coat hanger sights, and fires before anyone can stop him. Direct hit. The impact mark appears clearly on the Panzer's painted hull. Before the tank completes its turn, Skinner grabs the launcher and fires again. Another direct hit. The assembled officers and engineers rush over to see what just happened. This crude weapon, obviously assembled from spare parts that morning, just accomplished what 5 professionally designed systems failed to do. Hit a moving target twice. Major General Barnes examines the launcher. He asks Skinner what it is. Skinner explains the tube concept, the rocket motor specifications, the shaped charge warhead configuration. Barnes, who has spent months reviewing anti-tank weapon proposals that don't work, makes an instant command decision. He takes the launcher from Skinner, shoulders it himself, and fires at the Panzer. Another direct hit. The remaining officers fire the rest of Uhl's rockets. Every shot connects. 6 impacts total on a moving target at combat range, using sights made from a bent coat hanger. The accuracy speaks for itself. More importantly, the weapon requires no special training. Officers who never saw the launcher before are hitting tanks on their first attempt. Barnes, according to Skinner's account, makes one comment that names the weapon forever. It looks like Bob Burns's bazooka. Bob Burns is a radio comedian popular in the early 1940s who plays a homemade musical instrument he calls a bazooka, essentially a modified pipe that makes ridiculous sounds for comic effect. The launcher, 5 feet of tube with a hand grip and stock, bears undeniable resemblance to Burns' contraption. The nickname sticks immediately. Officially, the weapon becomes the 2.36-inch rocket launcher M1. Everyone calls it the bazooka. Here's what happens next, and this is where the story becomes about more than just clever engineering. This is about institutional decision-making under desperate time pressure. Barnes sees instantly that the bazooka solves the infantry anti-tank problem. It's portable, 13 pounds unloaded. It's simple, requiring minimal training. It's effective, demonstrably capable of hitting moving targets at combat range, and most critically, it can be manufactured immediately using existing industrial capacity. Within days, the launcher is demonstrated to General George C. Marshall, Army Chief of Staff. Marshall orders 5,000 units on the spot. The contract goes to General Electric's Bridgeport, Connecticut facility on May 20th, 1942. Deadline, June 14th. 25 days to deliver 5,000 bazookas and 25,000 rockets. This production schedule is insane by normal military procurement standards. Weapon development typically requires months of testing, design refinement, tooling preparation, contractor bidding, production ramp-up. The bazooka program compresses all of that into 3.5 weeks. General Electric receives technical drawings on May 20th that are barely more detailed than Skinner's original sketches. The launcher is fundamentally simple, which helps. A steel tube 54 inches long, 2.36 inches in diameter to match the M10 warhead dimensions. 2 hand grips, one containing the electrical, firing mechanism, a wooden shoulder stock housing 2 batteries. Wire sights, a simple contact system connecting the batteries to an ignition wire in the rocket motor. No precision machining required. No exotic materials, just steel tubes, basic electrical components, wooden stocks, and assembly labor. General Electric already manufactures electrical equipment, so the firing mechanisms present no challenge. The steel tubes are sourced from suppliers producing pipe for industrial applications. The shoulder stocks are cut from standard lumber using existing woodworking equipment. The E.G. Budd Company receives the contract to manufacture M6 heat rockets. These are more complex than the launcher. Each rocket consists of the M10-shaped charge warhead, a solid fuel motor, stabilizing fins, and an electrical ignition system. The shaped charge requires precise copper cone geometry to generate the armor-piercing jet effect. The rocket motor must burn at exactly the right rate to exit the launcher at proper velocity. The fins must deploy correctly to stabilize flight. Budd Company engineers work around the clock designing production tooling. The shaped charges are formed using hydraulic presses that stamp copper sheet into conical shapes with tolerances of thousandths of an inch. The rocket motors are cast in molds, then filled with solid propellant formulated to burn for exactly 1/50th of a second. The fins are stamped from sheet metal and riveted to the rocket body. The electrical igniters are assembled by hand, each one tested before installation. Meanwhile, at Bridgeport, General Electric sets up assembly lines for the launchers. The production process is remarkably straightforward compared to most military hardware. Steel tubes arrive pre-cut to 54 inches. Workers install the front hand grip, the rear pistol grip with trigger mechanism, the electrical contact box, and the wooden shoulder stock. Each complete launcher assembly requires approximately 45 minutes of labor. Quality control involves visual inspection and electrical continuity testing. By June 14, 1942, General Electric completes the order with 89 minutes to spare, 5,000 M1 bazookas ready for shipment. The Bud Company delivers 25,000 M6 rockets on schedule. The entire development cycle from Aberdeen demonstration to delivered weapons, 60 days. 2 months from prototype to production hardware in soldiers' hands. This timeline is unprecedented. For context, the M1 Garand rifle, adopted in 1936, required 8 years of development and refinement before full production began. The M4 Sherman tank, which will become America's primary armored vehicle, is still working through production challenges in mid-1942 despite 2 years of development. The Bazooka goes from scrap metal prototype to 5,000 delivered units in the time it takes most weapons programs to complete initial design reviews. But speed creates its own problems. The M1 launcher and M6 rocket enter production before extensive field testing reveals design flaws. The M6 rocket is notoriously unreliable. The electrical ignition system frequently fails. The rocket motor sometimes doesn't burn completely, causing the projectile to tumble in flight or fail to detonate on impact. The shaped charge warhead occasionally detonates prematurely if the rocket strikes at a severe angle. The launcher itself has structural weaknesses. The steel tubes are manufactured without precise bore gauges, meaning dimensions vary slightly between units. Some tubes are too narrow, causing rockets to stick during firing. When a rocket jams in the tube and the motor burns, the result is catastrophic. The tube explodes, killing or severely injuring the operator. Army Ordnance knows about these problems. They have reports from initial field testing showing failure rates above 30% for early production rockets. But the strategic situation doesn't allow time for fixes before deployment. American forces are preparing for Operation Torch, the invasion of North Africa scheduled for November 1942. Infantry units need anti-tank weapons regardless of reliability issues. The alternative is sending soldiers into combat with no armor-killing capability at all. So the bazookas ship. 600 M1 launchers go to British forces in Egypt in September 1942. 3,000 launchers are allocated to Soviet forces under Lend-Lease. The remaining units are distributed to American infantry divisions training for North Africa. None of these shipments include comprehensive training manuals. Some don't include any instructions at all. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The night before Operation Torch landings, November 7, 1942, General Dwight Eisenhower learns from a subordinate that none of his assault troops have received training on the bazooka. 0 training. Soldiers discover crates labeled Launcher, Rocket, Anti-Tank, 2.36-inch, M1, while unloading supply ships in the hours before hitting the beaches. They open the crates, find these strange tube weapons, locate the rocket ammunition, and try to figure out how everything works without manuals or demonstrations. Some units use bazookas during the landings against Vichy French positions. The weapons work intermittently. Some rockets fire perfectly, streaking toward targets and detonating on impact. Others fail to ignite. Others ignite but tumble in flight. Still, others detonate prematurely. One soldier's account describes firing 3 rockets at a French bunker. The first rocket doesn't ignite at all. The second fires but veers wildly off course and explodes in sand 30 yards away. The third hits the bunker and blows through 2 feet of reinforced concrete, stunning everyone watching. This unreliability defines the bazooka's combat debut. When it works, it's devastating. A properly functioning M6 rocket can penetrate 76 millimeters of armor, enough to disable any tank Germany deploys in North Africa during late 1942. The shaped charge jet burns through steel like a blowtorch cutting butter, creating a hole the diameter of a fist and sending molten metal into the crew compartment. Tanks hit by bazookas typically brew up within seconds as ammunition or fuel ignites, but the 30% failure rate means soldiers cannot trust the weapon. If you have one shot before a Panzer's machine gunner kills you, and that shot has a 3 in 10 chance of simply not working, you're gambling your life on unreliable hardware. This is unacceptable in combat, where trust in equipment means the difference between aggressive tactics and hesitation that gets people killed. The German military captures several M1 bazookas during the North Africa campaign and from Soviet forces who received Lend-Lease shipments. German intelligence immediately recognizes the potential despite reliability problems. They reverse engineer the design, increasing the warhead diameter from 60 mm to 88 mm for greater armor penetration, and create the Panzer Schreck. The German version proves more reliable and more powerful than the American original. This creates an embarrassing situation where German copies of American designs outperform the originals. By mid-1943, American soldiers are facing Panzer Schrecks that can reliably penetrate 180 mm of armor, while their own bazookas struggle to hit 90 mm. Army ordnance faces mounting pressure to fix the M1's problems or lose credibility with troops who need these weapons to survive. The solution arrives in stages. First, General Electric suspends M1 production in May 1943 to address tube quality issues. They wrap tubes with half-inch steel wire to prevent bursting failures. They implement bore gauges to ensure consistent internal dimensions. They eliminate the front contact box, which proved to be a structural weak point. This improved model becomes the M1A1. Simultaneously, engineers redesign the M6 rocket into the M6A3 variant. The new design features a rounded nose instead of the pointed original, which tended to deflect off sloped armor. The rocket motor receives a new propellant formulation that burns more consistently across temperature ranges. The electrical ignition system is simplified and made more robust. Most importantly, the M6A3 includes a cylindrical tail fin assembly that resists bending during transport and rough handling. These fixes work. By late 1943, bazooka reliability improves dramatically. The M6A3 failure rate drops below 5%. Soldiers begin trusting the weapon enough to build tactics around it. The penetration capability reaches 100 mm under combat conditions, sufficient to defeat Panzer III and Panzer IV tanks with frontal hits at ranges under 100 yards. Sicily, July 1943. The 36th Infantry Division lands with M1A1 bazookas and improved rockets. Rangers under Lieutenant Colonel William Darby report 11 confirmed tank kills during the first 3 days of fighting. One famous engagement involves a bazooka team scoring an improbable hit on a Tiger tank through the driver's vision slot, killing the driver and forcing the crew to abandon the vehicle. The Tiger is otherwise invulnerable to M1A1S from the front, with 100 mm of armor, but the vision slot hit demonstrates that skilled operators can exploit weaknesses. Anzio, January 1944. German counterattacks throw heavy armor at the beachhead, including Tigers and Panthers. American infantry rely heavily on bazookas for close-range defense. Private First Class. James Arness, later famous as the actor who played Marshal Matt Dillon in Gunsmoke, serves as a bazooka gunner. His account describes stalking a Tiger through rubble. You knew if you got the shot off clean, you'd kill it. That confidence kept you alive because you weren't panicking, just working. Normandy, June 6, 1944. Every American infantry company hitting Utah and Omaha beaches carries at least 4 bazooka teams. The weapons prove essential not just against armor, but against fortified positions. The shaped charge jet can blow through concrete gun emplacements. After-action reports from the 29th Infantry Division note bazooka teams clearing 12 pillboxes on Omaha Beach during the first 6 hours, allowing infantry to push inland past prepared German defences. Operation Cobra, late July 1944. The breakout from Normandy's hedgerow country. American divisions advancing through dense terrain encounter German armour ambushes constantly. Bazookas excel in this environment. Close-range surprise engagements where portability and first-shot effectiveness matter more than maximum range. The 4th Infantry Division logs 37 confirmed armour kills with bazookas during Cobra's first week. Tank destroyers and Shermans get most credit in official reports, but infantry journals tell a different story. Bazooka teams often kill German tanks before friendly armour even arrives at the contact. Battle of the Bulge, December 1944. German Panzer and Tiger tanks smash through American lines in fog and snow. Isolated infantry units defend crossroads and towns with bazookas as primary anti-tank weapons. At Bastogne, the 101st Airborne uses M9 launchers, an improved two-piece design introduced in October 1943 to knock out at least 18 German tanks during the siege. Captain James O'Neill, company commander with the 502nd Parachute Infantry, reports his men ambushing a Katora Panther column on December 22nd, killing 3 tanks in under 2 minutes by hitting them from building positions at 30 yards. Technical Sergeant Forrest Guth, who fights from Normandy to the Rhine, explains it simply in a 1945 interview. Before rifling, you fired and hoped. After rifling, you fired and knew. He's referring to a modification made in January 1943 that dramatically improved accuracy, but that's another story. The point is that soldiers learned to trust bazookas. The weapon became reliable enough to base tactics on, rather than treating it as a desperation option. By the time American forces crossed the Rhine in March 1945, bazookas have accounted for over 800 confirmed German armour kills in the European theatre. That 800 number tells only part of the story. The real revolution happens in how armies think about infantry anti-armour weapons. Before bazookas, portable rocket launchers were experimental gear that might work under ideal conditions. After Aberdeen's May 1942 demonstration, they become primary weapons that infantry commanders build entire tactical doctrines around. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The bazooka's 60-day development timeline becomes legendary in military procurement circles, but the story everyone remembers obscures what actually made it revolutionary. It wasn't just speed. It was the willingness to deploy imperfect solutions under impossible pressure and then fix them in the field while combat continued. Let's talk about what happened after those first 5,000 bazookas shipped. The production numbers tell one story. By the end of 1943, American factories had manufactured over 112,000 M1 and M1A1 launchers. By war's end in August 1945, total production exceeded 440,000 units. The rockets, millions of them, came from multiple contractors working around the clock. But raw production numbers miss the engineering evolution happening in parallel with combat deployment. Every battle generated after-action reports. Every report identified specific failure modes, and Army Ordnance responded with modifications that fed back into production within weeks, not months. This iterative improvement cycle, combat feedback directly informing design changes, became standard practice for American weapons development. The M9 bazooka, introduced in October 1943, exemplifies this approach. Airborne divisions requested a more portable version for paratroopers who needed to carry anti-tank capability but couldn't manage a 54-inch tube while jumping from aircraft. Engineers created a two-piece design that broke down into sections 31.5 inches long. This reduced length for transport while actually increasing the tube's overall length slightly, extending effective range by 50 yards. The M9 incorporated other lessons from 18 months of combat experience. The wooden shoulder stock was replaced with a wire rest, reducing weight and cost while simplifying production. The electrical firing system was redesigned for better reliability in wet conditions after soldiers reported ignition failures in rain and snow. The sights were improved based on feedback from troops who'd been aiming these weapons at moving targets under fire. Production of the M9 began slowly, just 26,000 units before an improved M9, a one variant superseded it. The M9A1 became the definitive World War II bazooka, with 277,000 units produced. This was the weapon that fought through France, Belgium, and Germany in 1944 and 45. By then, soldiers had developed sophisticated tactics around bazooka employment. Standard doctrine called for two-man teams. The gunner carried the launcher and aimed. The loader carried rockets, typically 6 rounds in a carrying bag, and handled the loading sequence. In combat, the loader would prepare the rocket, ensuring the ignition wire was properly connected, then insert it into the rear of the tube. The gunner would aim, announce up, and the loader would tap the gunner's helmet to signal ready. The gunner would fire, and both soldiers would immediately relocate because the backblast signature gave away their position. Skilled teams could fire 3 aimed shots per minute. This rate of fire meant that a single bazooka team could engage multiple targets in quick succession or put multiple rockets into a single target to ensure a kill. The Germans learned to fear bazookas in close terrain where American infantry could set up ambush positions with clear sight lines to roads and approaches. The Ardennes offensive tested everything. When German armor broke through American lines in December 1944, isolated infantry units found themselves as the only defense against Panther and Tiger tanks in conditions where supporting armor and anti-tank guns had been overrun or bypassed. Bazookas became the primary tank-killing system for units like the 101st Airborne at Bastogne. The cold created new problems. Rocket motors designed for temperate climates sometimes failed to ignite properly in sub-zero temperatures. The batteries in the firing system died faster in extreme cold. Soldiers learned to keep batteries warm inside their uniforms and only install them immediately before firing. They learned to pre-warm rockets near fires before loading them. These field-expedient solutions kept bazookas functional in conditions that paralyzed other equipment. The siege of Bastogne produced dozens of documented bazooka kills. Staff Sergeant Curtis Lalonde's team knocked out 3 German tanks on December 23rd by positioning themselves in a destroyed building overlooking the main road into town. They waited until the lead Panzer was within 40 yards, fired, hit it in the engine deck, then shifted position and killed the second tank with a side hit. The third tank retreated before they could engage it. Lalonde's team relocated 3 times during the engagement to avoid German infantry who'd spotted their backblast. Private Kenneth Hessler, also at Bastogne, described firing 8 rockets over 2 days of fighting, 5 hits, 3 confirmed kills. His account mentions the psychological impact. Once the Germans knew we had bazookas, they'd button up their tanks and proceed more cautiously. That caution gave us time to prepare positions and coordinate with other teams. Even when we didn't kill a tank, we slowed their advance enough for our defences to organise. The bazooka fundamentally changed how infantry fought armour. Before 1942, foot soldiers facing tanks had 2 options: hide and hope friendly armour arrived, or die trying to get close enough for desperate close assault with explosives. After bazookas became standard equipment, infantry could actively defend positions against armoured attacks. This changed tactical planning at every level. Division commanders knew their infantry could hold against limited armor attacks without immediate tank destroyer support. This freed up mobile anti-tank assets to respond to major breakthroughs, rather than being tied to static defense. Battalion commanders could assign bazooka teams to key terrain and expect those positions to survive armored reconnaissance. Company commanders used bazookas offensively, tasking teams to hunt disabled tanks or ambush supply vehicles. The Germans responded by developing countermeasures. Schürzen, spaced armor skirts mounted on Panzer sides, became standard after 1943. The skirts caused shaped charge jets to detonate prematurely, dissipating energy before reaching the main armor. This reduced bazooka effectiveness by 40 to 60% against side hits. But it also added weight and complexity to German tanks, reducing mobility and increasing maintenance requirements. German tank doctrine evolved to avoid close terrain, where bazookas thrived. They preferred open ground engagements at ranges beyond effective bazooka distance. But Normandy's hedgerows, the Ardennes forests, and German towns turned into battlefields, all favored American infantry with close-range weapons. The more the war moved into urban terrain during the final year, the more dangerous bazookas became. By early 1945, American industry was already working on the next generation. The 3.5-inch M20 Super Bazooka entered development in late 1944, when it became clear that German King Tiger tanks, with their 180 mm of frontal armor, required more powerful weapons. The M20 used 90 mm rockets with dramatically improved shaped charge warheads, capable of penetrating 180 to 280 mm of armor. The M20 wasn't ready before Germany surrendered in May 1945. Post-war budget cuts delayed its adoption until 1950, when North Korean T-34 tanks crossed the 38th parallel and American troops in Korea discovered their stored M9A1 bazookas and degraded M6A3 rockets couldn't reliably stop Soviet-built armor. The ammunition had deteriorated in storage, and the penetration capability was marginal against T-34 seconds, even with fresh rockets. The disaster at Osan on July 5, 1950, where Task Force Smith's bazookas repeatedly bounced off T-34 seconds, forced emergency deployment of M20 Super Bazookas to Korea. These weapons finally gave American infantry reliable tank-killing capability against modern Soviet armor. After-action reports from the Pusan perimeter fighting in August 1950 show bazooka teams accounting for 41 T-34 kills in 2 weeks once M20S reached the front lines. The technology continued evolving. The M72 LAW, light anti-tank weapon, adopted in 1963, was essentially a disposable bazooka in a pre-loaded tube. Soldiers fired it once and discarded the launcher. This eliminated the reload sequence vulnerability and reduced weight. The M72 used the same basic principles Skinner and Uhl discovered in 1942. Tube-launched rocket with shaped charge warhead, just refined over 2 decades of development. Modern systems trace direct lineage to Aberdeen Proving Ground in May 1942, the AT-4, adopted in 1987. The SMAW, shoulder-launched multi-purpose assault weapon, fielded in 1984. Even the Javelin missile system, with its sophisticated guidance and top attack capability, launches from a tube that vents exhaust backward, using principles identical to the original bazooka. The 60-day development timeline remains unmatched in modern military procurement. Current weapons programs measure development in decades. The F-35 fighter jet, from concept to initial operational capability, took 20 years. The Zumwalt-class destroyer, 15 years. The Army's Future Combat Systems program spent 18 years and $20 billion before cancellation without producing a single deployable system. Why could Skinner and Uhl design, test and field a revolutionary weapons system in 2 months when modern programs require decades? Part of the answer is wartime urgency. When infantry are dying for lack of equipment, bureaucratic delays become unacceptable. Peacetime procurement prioritizes minimizing risk and maximizing oversight, which extends timelines but reduces the chance of expensive failures. But there's a deeper factor. The bazooka was fundamentally simple. Steel tube, electrical trigger, rocket motor, shaped charge. No sophisticated electronics, no complex materials, no precision machining beyond basic industrial capability. Simplicity enabled rapid development because there were fewer points of failure and fewer components requiring coordination between contractors. Modern weapons systems are vastly more complex. They incorporate computers, sensors, guidance systems, encrypted communications, and sophisticated materials. This complexity delivers performance that World War II engineers couldn't imagine. But complexity also multiplies development time and cost. Every subsystem requires integration testing. Every component needs multiple suppliers for production redundancy. Every interface creates opportunities for incompatibility. The bazooka succeeded because two engineers looked at a problem, identified a solution using available technology, and implemented it without overthinking the process. The shaped charge existed. The rocket motor existed. The steel tube existed. Nobody had combined them in exactly this configuration. The innovation was assembly, not invention. This pattern repeats throughout World War II, American industrial achievement. The Manhattan Project produced atomic weapons in 3 years by assembling existing physics, knowledge, and industrial processes in new configurations. The Liberty ship program built 2,700 ocean-going cargo vessels in 4 years using standardized designs and mass production techniques adapted from automobile manufacturing. The B-29 bomber went from initial concept to combat deployment in 4 years, despite being the most technologically advanced aircraft of its era. Speed required accepting risk. The M1 bazooka deployed with known reliability problems because the alternative was no bazookas at all. Soldiers died because rockets failed to ignite or tubes burst. These deaths were weighed against larger numbers who would die without any anti-tank capability. The calculation was brutal but necessary in wartime. Modern procurement culture avoids this calculus. No program manager wants to be responsible for deploying equipment that kills the soldiers using it. So, testing extends. Requirements multiply. Design reviews proliferate. And years pass while perfect solutions are pursued that will never face the urgency that made imperfect solutions acceptable in 1942. Skinner retired as a colonel in 1956. Uhl left active duty after the war and worked in aerospace engineering. Neither became famous. Most histories of World War II weapons mention the bazooka briefly, if at all, usually as a footnote to discussions of armor tactics or infantry equipment tables. But every American infantryman who carried a tube-launched anti-tank weapon from 1942 through Vietnam benefited from what Skinner and Uhl accomplished in 60 days. The bazooka gave foot soldiers the ability to fight armored vehicles on approaching equal terms. It made infantry positions defensible against tanks. It changed tactical doctrine across every army that observed its effectiveness. The Germans copied it. The Soviets developed their RPG series based on the same principles. The British created the PIAT as a spring gun alternative, then adopted tube-launched rockets post-war. The French developed their own versions. Chinese forces used captured bazookas and Panzer Shreks in their civil war, then produced indigenous copies. By 1950, tube-launched anti-tank rockets were standard infantry equipment worldwide. This diffusion happened because the basic design worked and couldn't be kept secret. Once Germans captured bazookas in late 1942, the technology became available to anyone with basic industrial capacity. The physics of shaped charges was published in scientific literature. The rocket motor chemistry was straightforward. The tube launcher required no proprietary manufacturing. Any nation with a steel industry could build bazookas. The legacy extends beyond hardware. The 60-day bazooka program demonstrated that rapid weapons development was possible when institutional barriers were removed. It showed that combat feedback could drive iterative improvement faster than laboratory testing. It proved that simple solutions to complex problems sometimes outperform sophisticated alternatives. These lessons influenced post-war American military procurement, though with mixed success. The Pentagon during the Cold War tried to institutionalize rapid development through programs like the Advanced Research Projects Agency, but complexity crept back in as technology advanced. By the Vietnam era, weapons programs once again measured timelines in years rather than months. The Bazooka stands as a historical anomaly, a moment when desperation, engineering talent, industrial capacity, and bureaucratic support aligned perfectly to produce extraordinary results in minimal time. The circumstances that enabled 60-day development from prototype to fielded weapon were unique to World War II's emergency conditions and cannot be replicated in modern contexts. But the principle remains valid. When survival requires innovation, institutions can move faster than anyone believes possible. Two engineers with a scrap metal tube and a brilliant idea changed infantry warfare forever. They did it in 2 months. And they did it because waiting wasn't an option. The morning of May 14th, 1942, General Barnes watched a coat-hanger sight guide a rocket into a German Panzer and understood he was seeing the future of infantry combat. 60 days later, 5,000 of those launchers were in soldiers' hands. By war's end, the bazooka had become as iconic to American infantry as the M1 rifle, and it all started with Lieutenant Uhl walking past a scrap pile and recognizing that a piece of discarded pipe could kill tanks. That's the story of how engineers designed the bazooka in 60 days and made infantry stop Panzer attacks alone, not through perfection, but through speed. Not through sophisticated technology, but through simple effectiveness. Not through eliminating risk, but through accepting it in service of solving an immediate crisis. 60 days, from junkyard inspiration to weapons that changed warfare. 60 days that proved desperation and talent could accomplish what peacetime bureaucracy never would. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.